أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم Alhamdulillah, thanks to Allah subhanahu wa ta'ala for all his blessings and bounties that he has bestowed upon us. فَبِأَيِّ آلَاءِ رَبِّكُمَا تُكَذِّبَانِ. We should make sure to Allah subhanahu wa ta'ala that he has created us as a mankind, the best of all the creations, the Ashraful Makhluqat. On top of that, he has created us in the Ummah of Muhammad sallallahu alayhi wa sallam, the best of all the Anbiya of Islam. They came to existence to guide the humanity so that each and every mankind could be successful not only in this life but the life hereafter. We should make shukr to Allah subhanahu wa ta'ala that he has given us Iman, to believe Allah subhanahu wa ta'ala with all his powers, with all his control, with all his qualities. It comes in Hadith more or less meaning. Iman has more than 70 branches. The exteriormost is the one of saying La ilaha illallah. There is none worthy of worship except Allah subhanahu wa ta'ala. And the inferiormost is the one of removal and obstacle from the way. Modesty. Haya is also a branch of Iman. So today we are going to talk about a very last topic, in fact. I mean, it depends if time permits. We can go back to extend our previous topics, or that one, the existing one, Fourier series, as much as we can. But anyway, for the time being, we are going to talk about the fourth component of this course, Fourier series. We will develop a solution in the form of a series. Certain criterions are there, as we have discussed over the previous weeks, and that different criterions are there for different types of techniques to be implemented. Before we implement certain technique, we will have to fulfill certain criterions. If all the criterions are fulfilled, only then we can move into that particular theory. Otherwise, we have to look into the alternative options. A very powerful technique is there to find, to solve, to obtain the solution of a certain physical phenomena behind the scene. Phenomena again is going to be described mathematically in the form of an expression. Based upon that, we will look into the solution as a series known as Fourier series. If we look into the description, periodic functions are going to be one of the criterion. The function has to be periodic behind the scene. The mathematical equation, the expression of f should be periodic. And we know that function is said to be periodic. If we look into the geometry of that function, it does repeat itself in finally many times. So repetition is there. If you take a certain portion of the graph, graphically, if you look into that, mathematically there is a definition. What does this mean by a periodic function? But graphically, if you take a certain portion of the graph, so you see that it is going to be repeated over and over again. So periodic functions, they occur quite frequently in engineering problems. Their representation in terms of simple periodic functions like sine and cosine is a matter of great importance, which leads to Fourier series, because the whole series is heavily based upon those trigonometric functions sine and cosine. Fourier series is going to be very powerful tool in solving various problems involving partial differential equation in particular. The theory of Fourier series is rather complicated. I mean, you will see that. Yes, when we look into the development, when we look into the construction, or we are interested to calculate the coefficients of the series, things are a bit demanding behind the scenes. But when we look into the implementation of the series, it is going to be quite simple. And since we are more interested at this time in the implementation, so this is going to be much easier part in comparison of the development, the construction. We will also try to take a glimpse of idea behind the scene. But anyway, we will more focus on the implementation in this particular topic. Fourier series are, in a certain sense, more universal than Taylor series, and we all know about Taylor series. Taylor series is basically regarded as the backbone of applied mathematics. Every numerical technique, every numerical method is heavily based upon the concept of Taylor series expansion. Whenever we are trying to observe the quality in terms of error, we have to compare every numerical technique, every numerical method with the Taylor series expansion. So this is how we say that Taylor series is regarded as the backbone of applied mathematics. Inside mathematics, we say that numerical analysis is going to be an essential component. But we say that if you look into this series, the Fourier series, we say that in some sense, it is more universal than the Taylor series, because many discontinuous periodic functions of practical interest can be developed only in the form of Fourier series. So this is all. When we see a certain phenomena is there, discontinuity is there with periodic functions, we will look into the Fourier series to get an idea about the behavior of the phenomena in the form of a solution, which is going to be a series solution, of course. So first of all, we give some basic definitions which will be used in our later work. The very first definition, periodic function. As I said earlier, graphically, geometrically, if you see a periodic function, it states that after a certain period, you repeat the same portion of the graph identically over and over again. Mathematically, we say that if there is a constant, the positive constant p, such that f of x plus p is equal to f of x. So f of x is the original function. You replace x by x plus capital P. P is going to be some positive constant, but you get the original function back, f of x, for any sort of value of x. We say that, yes, f of x is a periodic function. What the period of the function is? P. It is then called as period of that function, f of x. So mathematically, f of x plus p should be equal to f of x. Graphically, we are interested to see the geometry, the graph of a such function is obtained by a periodic repetition of its graph in any interval of length capital P. I mean, that portion of the graph, whatever the value of P is there, you will see that there is a periodic repetition over and over again. The same graph is going to be repeated. Take an example of periodic function, for example, as an example, that one. In the x1 plane, x-axis, y-axis is there, and we will be having a graph like that. Oscillation is there. And we say that this is going to be the period from this point to that point. Because if you take that portion of the graph, you will see that yes, it is going to be repeated again. It is repeated before and after in this particular case. But anyway, this portion of the graph, that one, is going to be repeated over and over again. So we say that P is going to be the period. Function is periodic and P is going to be the period. Are there any other periods? Are there any other chances to have a period different from P? Yes. If you extend the graph on both sides and then look into that portion, for example, from here to there, for example. You will see that yes, this is going to be another period.
देखिए कितने मेरी वॉइस कर रहा हूँ
All of them are mute now. All right. So we go back. Yes, this is going to be another period. If you take that portion of the graph from this point to that point, because this portion of the graph is also going to be repeated over and over again. So there are chances, yes, we could have more than one periods of one periodic function. But the least period, the least positive value of P is going to be the period or the fundamental period. We'll look into that in a minute or so. It is easy to verify that if P is a period of f of x, then 2P is also a period of the same function f of x. Because in general, if n is a positive integer, then np is also going to be a period of that function f of x. That is f of x plus np is equal to f of x. What is n? Any positive integer. So p is going to be a positive constant, n is going to be any positive integral value. So we say that if f of x is a periodic function, then not only p, but also 2p, 3p, 4p, they could also be the periods of that particular function f of x. The least period of f of x is called the fundamental period. As in this case, p is the starting period. Then of course we look into 2p, 3p, 4p, and then so on. So we regard capital P or 1 times p as the fundamental period, or simply we say that this is going to be period. More than one chances are there, but the least value or the least period of f of x is going to be the period or fundamental period of a periodic function f of x. Take some examples. The most vital is to be discussed trigonometric functions sine and cosine, because the Fourier series is heavily based upon those trigonometric functions sine and cosine. So the function sine of x, we say that it is periodic. Mathematically, if you replace x by x plus something, in the generalized case that something was p. Now if p is equal to 2 pi, we see that yes, sine of x plus 2 pi is equal to sine of x. P is equal to 2 pi in this case. Not only sine of x plus 2 pi, but also sine of x plus 4 pi equal to sine of x. Sine of x plus 6 pi is again sine of x. So we say that yes, more than one periods are there, 2 pi, 4 pi, 6 pi, and then so on. But what is the period or fundamental period of sine? N is going to be 2 pi, because this is going to be the least period of sine of x. Pretty much on the same line, we see that cosine of x is also having period 2 pi, whereas tan of x is having period pi, the fundamental period. Because if you look into cosine of x plus 2 pi, you will get cosine of x and tan of x plus pi. Simplify that by utilizing the formula behind the scene, like tan of a plus b, tan of a plus tan of b upon 1 minus tan a tan b. A is equal to x, b is equal to pi in this case. So if you do simplify this one, eventually it is going to be x, tan of x. So tan of x plus pi is equal to tan of x. It means that yes, pi is going to be period or fundamental period of tan. More generally, if you are interested to see fundamental period of sine nx and cosine nx, where n is going to be positive integral value, so we say that it is going to be 2 pi upon n. So 2 pi upon n is going to be fundamental period of sine of nx as well as of cosine of nx. So what we have to do, if you need to prove that 2 pi upon n is going to be period of sine of nx, so this is going to be f of x. We need to replace x by x plus 2 pi by n. So sine of nx is going to be sine of n times x plus 2 pi upon n. X is being replaced by x plus 2 pi upon n. Then simplify that, sine of nx plus 2 pi. Expand this one, and we know that sine of 2 pi is going to be 0, cosine of 2 pi is 1, second term is vanished, and from the first term we're left with sine of nx. So sine of n x plus 2 pi upon n is equal to sine of nx. Same is the case with cosine of nx. If you replace x by x plus 2 pi upon n, again you will get cosine nx. So generally, with n being a positive integral value, the period of sine nx and cosine nx is going to be 2 pi upon n. If you take n is equal to 1, of course, you talk about sine of x. So sine of x plus 2 pi eventually will be equal to sine of x. And you could also take different values. But make sure n is going to be positive integral value. A constant function will also be regarded as a periodic function in the sense of definition. What the definition is there? There are two definitions, remember. One is the mathematical definition, the other one is the geometry, the graphical representation. What we have to see in graphical representation, that a certain portion of the graph is going to be repeated over and over again. But when we talk about mathematical formulation, we say that for any periodic function f of x plus p should be equal to f of x. Now, since f of x is a constant value, it is not going to be changed. Whatever the change that you make in the value of x. Like f of x is equal to c means that it's a straight line parallel to the line x-axis. So parallel to the line x-axis, whatever the value of x is there, the graph is not going to be changed. Horizontal, straight line parallel to the line x-axis. The distance to y-axis will remain the same, whatever the value of x is there. I mean, if you make a change in the value of x, the outcome is not going to be changed, and that's what is the definition. The value of f of x and of f of x plus p is identical. So this is how we say that f of x plus p is equal to f of x. Does satisfy the mathematical definition of a periodic function. But there is a trouble behind this one. What the trouble is here? There won't be any fundamental periods of a constant function. Why so? I mean, we are interested to see, for example, we are interested to see the geometry. So let me do that. Just to take a glimpse of idea behind the scene. All right, so here you go with a constant function. It's a constant function now. I mean, you can extend your journey as much as you can. But what is going to be the period? I mean, it all depends what portion of the graph that you are interested for. This is going to be a period. Yes, we are agreed. This is going to be also period. Yes, we are agreed. Because this portion of the graph is also going to be repeated. But what is going to be the smallest period? There is no certain value. I mean, just in the loose sense, if you think how many real values are there in between 0 and 1? Infinitely many. And what is the very next real value after 0? 0.001, 0.00001. I mean, infinitely many options are there. There is no certain value. So this is all. When we talk about a constant function, it's a constant function parallel to the line x-axis, has got a fixed distance from the line x-axis. So we have infinitely many options to describe its period. But what is going to be the smallest? There is no certain value. So this is how we say that. Thus, any positive number is a period of f of x. Since there is no smallest number to satisfy this criterion, f of x has no fundamental period. In case f of x is going to be a constant value. For a constant function, there is no fundamental period. We will be having infinitely many options, but there is no fundamental period. I mean, we are not sure how much of the smallest portion of the graph to be considered as a period. Graphically, we have seen that, and geometrically, we know that even in between 0 and 1, infinitely many real values are there. Examples of periodic functions which arise in engineering and physical sciences are, for example, the propagation of electric current in an alternating current circuit, mechanical vibrations, wave propagation in different types of media. A medium is, the surface that we talk about normally. What type of the surface is there? The displacement of a piston in a piston engine, the motion of the Earth about the Sun to very high accuracy with a period of 1 year. Remember, we talk about the accuracy when we are interested to find the orbital trajectory of the planet Earth orbiting around the Sun. In our solar system, there are 8 planets, starting from Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Together with Sun, it is going to be 9-body problem. The closest to Sun is going to be Mercury, and furthest is going to be Neptune. So, if you look into the orbital trajectory of the planet Earth around the Sun, so it takes 365.25 days. Not exactly 365 days. It will take 365.25 days to complete its orbital trajectory around the Sun. No, 0.25 is 1/4 of the day. So, but the criterion been set that after 4 years, you add 0.25, once more 0.25, 0.25, and then 4th time, if you add 0.25, it will turn out to be 1. So, the criterion been set to add 1 day after every 4 years. The year which is going to be divisible by 4 is known as leap year. And this is all. We adjust that fraction 0.25 on top of 365 days to very high accuracy. The time it takes to complete one orbital trajectory, orbital period, it takes 365.25 days for the planet Earth. So to adjust that, so we normally see the criterion behind the scene is to add 1 more day after every 4 years, and the day is added to the month of February. So when it's a leap year, the month of February is going to be of 29 days. Of course, we talk about accuracy and efficiency when we talk about the numerical aspects, when we talk about numerical solution of certain physical phenomena. And then, of course, we have different levels of accuracy. We look into the desired degree of accuracy while performing numerical approximation behind the scene. So this is all. As a precautionary measure to highlight the concept behind the scene to very high accuracy. If you do that, it will take approximately a period of 1 year. Not exactly 365 days, it's basically 365.25 days. The bending of a telephone cable which is suspended from regularly spaced poles is a function which is periodic with respect to the distance. But if you look into biology, the beating of heart under normal condition, what the normal condition is there? If a person is adult, 18 years or more than that, so then we see that, yes, the number of times heart is beating, it's in between 70 to 100. So yes, the repetition is there. If you go to the hospital and you will see that, yes, the heart beating is going to be observed. So it is going to be an oscillation. So you see that, yes, it is going to be observed. as a periodic function over there. So certain period of time it is going to be repeated over and over again. Whereas, if you look into the counter examples the other way around, examples of functions that are not periodic, like x. So f of x is equal to x is not going to be periodic. You can observe both by mathematically, what the definition is there. F of x plus p should be equal to f of x for some constant, positive constant p. So if f of x is equal to x, by replacing x by like x plus 1, you can never get back to the original function f of x equal to x. So it is going to be changed. And graphically, x is going to be a straight line passing through the origin. So we'll be having a portion in the first and third quadrant. So, you can never get the repetition of its portion of the graph if you look into the geometry of that graph. Same is the case with x square, x cube, and many more examples are there. So these are the examples where we see that the function is not going to be periodic. We now give some important integrals which are going to be utilized over and over again. Once the result is proved, no need to do it again. We just recall the basic concept and we will utilize it in our later work. For example, the integral of sine and cosine over the interval from minus pi to pi will always be equal to 0. The integral of sine kx from minus pi to pi is 0. The integral of cosine kx from minus pi to pi is also equal to 0. Now, once you prove them, no need to go and prove them again. So we will utilize them. Whatever the value of k is going to be non-negative integral value, positive integral value, in fact, 1, 2, 3. So if you look into the proof of one of the k sine kx, simple proof is there. So take its integral. It is going to be cosine with a negative sign. So cosine of kx upon k. So minus 1 upon k is adjusted outside. The interval is from minus pi to pi, means the upper limit is pi, the lower limit is minus pi. So apply the upper limit, the lower limit, we further know the trigonometric identity. Cosine of minus theta is equal to cosine of theta. So replace it, and eventually cosine of kx minus cosine of kx is equal to 0. So eventually we see that yes, this integral is vanished. Sine of kx is equal to 0 over the interval from minus pi to pi. Same is the case with cosine kx. Few more results you can look into the proof yourself. Simple criterions are there by utilizing those trigonometric relations from the previous or assumed knowledge. Cosine mx times cosine nx. So if you integrate over the interval from minus pi to pi with respect to x, so it is going to be 0 in case m and n are not equal to each other. But if they are equal to each other, so the result is going to be pi. For sine mx, sine nx again, the outcome is going to be 0 in case m is not equal to n, and pi if m is equal to n. Our alternative option is there, sine with cosine. So that will be 0 for all sort of values of mn, where m and n are going to be positive integers, 1, 2, 3, and so on. So these are simple results behind the scene. You can look into their proof. We have seen one of them, simple criterion, simple integration is there. Now we further look into some results which will be useful in our later work. So very powerful result is there, which is going to be utilized over and over again while talking about the Fourier series. We say that let f of x be a periodic function with period 2 pi, then the integral of f of x over the interval from minus pi to pi will be equivalent to integral of f of x over the interval from c to c plus 2 pi, but c is going to be an arbitrary constant. Means for any periodic function with period 2 pi, this interval can be replaced minus pi to pi with an arbitrary interval of period 2 pi. How do we observe the period? You see that upper limit minus lower limit. So pi minus pi, it is going to be pi plus pi equal to 2 pi. So c plus 2 pi minus c, it is going to be 2 pi. So they are equivalent to each other. So this theorem or this result, very powerful result is it, states that we can replace an interval from minus pi to pi by any arbitrary interval of length 2 pi. So the restriction is there. The length, the period should be 2 pi, but it can be replaced by an alternative period to make sure that the answer is identical. We will get the same answer as long as the period is going to be 2 pi. All right, we look into the proof of that. So take the right hand side. An integral of f of x over the interval from c to c plus 2 pi. So what we do, we utilize the fundamental theorem of integral. We subdivide the interval from c to c plus 2 pi into 3 subintervals: c to minus pi to pi, and then from pi to c plus 2 pi. So we have 3 integrals to the right hand side of equation number 6. So we take the last integral, that one. Integral over the interval from pi to c plus 2 pi. And in this last integral, we replace x by y plus 2 pi. We change the variable of integration. Now, since x is being replaced by y plus 2 pi, so everything has to be changed. Differential of x has to be changed. So if x is equal to y plus 2 pi, so then dx would be equal to dy. And x is going to be replaced by y plus 2 pi. The upper limit has to be changed. So corresponding to c plus 2 pi, yes, when x is c plus 2 pi, so c plus 2 pi will cancel and eventually y will be c. So with variable y, the upper limit will be c instead of c plus 2 pi. So this is c plus 2 pi is going to be replaced by c. When x is pi, the lower limit, so replace x by pi, so because everything has to be obtained from this substitution. When you replace x by pi, then y would be, take this 2 pi to the other side, so minus 2 pi plus pi minus pi. So the lower limit, pi is going to be replaced by minus pi. So this is, they are equivalent to each other. The left hand side is equivalent to that right hand side, where we replace x by y plus 2 pi, dx by dy, the upper limit c plus 2 pi by c, and the lower limit pi by minus pi. So invert or reverse or swap the limits, the lower limit becomes the upper becomes the lower limit. So we have to adjust the impact of that by adjusting a negative sign. So this is, an integral with negative sign from c to minus pi will be equivalent to the same integral, but with limits from minus pi to c. So if you topple or swap the limits, so you need to adjust the sign. So we have adjusted a negative sign. So f of y plus 2 pi dy over the interval c to minus pi. So we can do that in a way. If you look into this integral, we could change variable by using change variable property. If you have y over here, just replace it by z, no matter. we want to replace y by t no matter. There won't be any change in the limits or the expression. We just change the variable. So by changing variable y by x, so it will turn out to be something like that. So eventually, an integral from pi to c plus 2 pi would be equal to minus c to minus pi f of x plus 2 pi. And we know that f of x is periodic with period 2 pi. So f of x plus 2 pi would be equal to f of x. So replace f of x 2 plus 2 pi by f of x. So we will be having that. So this thing is equal to an integral from minus c to minus pi. So replace that last integral on the right hand side of equation number 6 by minus from c to minus pi f of x dx. So once we replace this one, the last integral to the right hand side by this expression, so we will be having equation number 6 like that. Now the last integral is identical to the first integral. Due to opposite sign, they are going to cancel each other effect, and we're left with this one. Minus pi to pi f of x dx would be equal to integral from c to c plus 2 pi f of x dx, or it could be written as. So hence, in this way, we prove that. What the message is there behind this? This theorem states that if f of x is a periodic function with period 2 pi, the interval of integration may be replaced by any other interval of length 2 pi. Very powerful result is there. So f of x is there, dx is there. What we do, we replace the interval of integration from minus pi to pi as c to c plus 2 pi. All right, before we move on, I generate a poll for attendance purpose in the meanwhile. No, n can't be negative. N has to be positive. It is defined over there. Attendance today is 7th of August. Yeah. 7/8/2020. And we are interested to see all present. The second option is there. All right, here you go. When the theory is developed, basically it is developed with more general cases. In some cases, some particular cases, yes, there could be a violation of the theory, but we do not regard them as a part of the theory. Chances are there, I mean, when we look into the theoretical aspect and see the restrictions are there, the constraints are there, so we have to fulfill them. For generalized case, generalized means high percentage of acceptability should be there, maybe 99%, 95%. So chances are there, sometime we could have special cases where we see that the theory is not going to work, but they are going to be neglected. On one side you have, for example, 1 billion cases that true following the theory. On the other hand side, you have 5, for example, violating the theory. So people normally pay attention to those 1 billion acceptable possibilities. So this is how they say that it is going to work in general for most of the cases. All right, so we move on. So yes, we have seen that. A very powerful result is there. If there is a periodic function with period 2 pi over the interval from minus pi to pi, so we see that it can be replaced by an arbitrary period, because C is going to be an arbitrary value, but we have to ensure that the length of the period is going to be 2 pi. As a very special case, if you take C is equal to 0, for example, then we will be having an interval from minus pi to pi equal to 0 to 2 pi. So same length, 2 pi minus 0 is equal to 2 pi, pi minus pi, it is going to be 2 pi. So everything is identical, f of x dx is there. Keep an eye on these aspects. Now we define Fourier series. So how do we find a solution of a periodic function in the form of a series? What the definition is there? What are the essential components that we have to observe? It states that if f of x is a periodic function of period 2 pi over the interval from minus pi to pi, the infinite geometric series f of x is equal to a naught upon 2 plus summation over the range from 1 to infinity. So means positive integral values, a and cosine nx plus b and sine nx. We have seen that cosine nx and sine nx, they will be having period of 2 pi upon n, where n stands for positive integral values. So it's called the Fourier series or Fourier expression of f of x if the coefficients an and bn are given by. So this is going to be a series. Series solution, what type of the series is this? It is going to be infinite geometric series. Unknown coefficients are there, a naught out of an, because n has to start from 1. So this is how it has been separated. A naught, and then we will be having an and bn in general. So these are the coefficients to be determined. Once we determine a naught, an and bn, plug in all these values here, expand them as much as you can. So this is going to be the series solution of f of x, provided that f of x is periodic function of period 2 pi. So what are those unknown coefficients? A naught would be an integral over the interval from minus pi to pi, 1 upon pi, multiple of that. An is going to be 1 upon pi times integral over the interval from minus pi to pi f of x cosine nx dx. And bn, everything is identical, only you need to replace cosine by sine. What is that? Positive integral value. The function f of x is called defining or generating function of the Fourier series, and the coefficients an and bn given by equation number 7 are known as Euler Fourier coefficients. There is a proof. I mean, we can calculate them, a naught, an and bn, by utilizing the fundamental aspects of the theory. But anyway, we leave it. The development or the construction of those coefficients, rather we will take as granted the definition. We will try to implement the definition to calculate the Fourier series in the form of an infinite series. So if you look into the message behind the scene, what we have to do, while looking into the series solution of a periodic function, only we need to calculate A naught, An, and Bn. Formulas are there. A naught is to be calculated from here, An and Bn from there. Once we have A naught, An, and Bn, so you need to plug in over here. So it will take us to infinite geometric series. And this is the simplest way. I mean, as we discussed earlier on at the start of this lecture, that theory is a bit complicated, a bit demanding when you look into the construction, theoretical aspects, but the implementation is rather simple. What the implementation is there, only you need to calculate A naught, An, and Bn. How do we calculate them? By utilizing those formulas. A naught is there, An is there, Bn is there. So just calculate them and plug in the formula. It will take you to the infinite series as a series solution to f of x being a periodic function. Change of intervals. Yes, we could also change the interval. We have seen one very powerful result behind the scene. If there is a function of period 2 pi from minus pi to pi, the interval of integration could be replaced by any suitable interval, provided that the interval length of the interval should be 2 pi. So same is the case we are going to look into that when we are going to talk about the coefficients, because again we have seen that the interval is utilized as from minus pi to pi. Since f of x is periodic function with period 2 pi, so f of x cosine nx and f of x sine nx are also periodic. Surely they are going to be periodic. Hence, the Fourier coefficients An and Bn can be determined equivalently from these integrals. For the integral form, for A naught, it's an integral over the interval from c to c plus 2 pi, c to c plus 2 pi, c to c plus 2 pi, where c is going to be some arbitrary constant. In the special cases, when c is equal to minus pi, for example. So if c is equal to minus pi, so minus pi and minus pi plus 2 pi, so it will turn out to be an interval from minus pi to pi, minus pi to pi, minus pi to pi. So yes, if you replace c by minus pi, so the interval of integration would be minus pi to pi in all these cases. Or if you take c is equal to 0, for example, very special case. So the interval of integration would be in this case from 0 to 2 pi, 0 to 2 pi, 0 to 2 pi. So here you go with the coefficients A naught, An, and Bn. So yes, they could be obtained, those coefficients of Fourier series. Even the interval of integration is different from minus pi to pi. But to make sure that the length of the interval is identical to pi, no matter whatever the starting and the ending point, whatever the lower and the upper limit is there, we are only interested to see the length of the interval. As long as the length of the interval is 2 pi, we can replace the interval from minus pi to pi by any other interval. Or if the interval is different from minus pi to pi, even then the Fourier series can be implemented. Because what the fundamental definition is there, it said that f of x is periodic of period p 2 pi defined over the interval from minus pi to pi. So this is going to be fundamental. But this interval from minus pi to pi could also be replaced by an interval from like 0 to 2 pi. As long as the length of the interval is 2 pi, we can find its solution by utilizing Fourier series. So here you go with few of the examples. Find the Fourier series of the following function which are periodic with period 2 pi. It's a piecewise function, of course, if you are interested to see its geometry. So on the line x-axis, it will be 0 from minus pi to 0, and then from 0 to pi, it will turn out to be 1. So 0 is there, and then 1 is there. So it is going to be repeated over and over again. 0 and then 1, 0 and 1 over the interval from minus pi to 0, and then 0 to pi again and again. So what the length of the interval is there? So how do we observe the length of the interval? It's pretty easy. Take the least value, smallest value, it's minus pi, and look into the greatest value, is pi. So pi minus pi, it is going to be 2 pi. So overall length is going to be 2 pi. Here you go, 2 pi minus 0. So for f of x, the length or the period is going to be 2 pi. So here you go again, you see that 3 pi by 2 minus pi by 2. So again 2 pi. The length of the interval is 2 pi, or the function is periodic with period 2 pi. So again you see that different intervals are there, but they are all of length 2 pi. So as long as the length of the interval is 2 pi, we are happy to utilize the Fourier series. How do we find the Fourier series? We know the formula behind the scene. In the formula, all we need to calculate A naught. All we need to calculate AN and BN. Once we have all these things, plug in those in the formula to calculate infinite geometric series of the given function. So in all these cases, we see that it's a piecewise function. Are they continuous functions? I mean, the pieces are continuous or not? Keep an eye. Think about that. The interval is from minus pi to 0. None of them are included, neither minus pi nor 0. Same is the case with this one. So would you believe that it is going to be continuous? Same is the case over here. Think about that. Greater than 0, less than pi, greater than pi, less than 2 pi, greater than minus pi by 2, less than pi by 2, greater than pi by 2 to 3 pi by 2, minus 1 is there and 1 is there, minus 1 and 1, minus 1 and 1 is there. So this is all. The repetition would be there. Repetition would be there. It is going to repeat itself over and over. All right, so you can try. Take them as your homework practice over the next few days. We will look into that. We will be having a makeup class, remember, on Monday, inshallah. Monday at 2 p.m. Internet connection at home is horribly being interrupted. So this is how we sometimes face problems with technology as I am facing nowadays. So I believe that it is going to be adjusted over the time. Sometimes you see unwanted interruption, distortion is there. All right, so that's it. So if you have any query, got some time, we can discuss.